Hi, welcome back to CS170 fall session. We're in the second video clip for week 2. We're going to give a quick introduction about digital or binary representation as well as hex representation. So you can see here the idea of a PandA representation, which is presence and absence, the binary system, hex notation, binary compared to decimal. We'll get into conversions. The conversions bit I'm probably going to separate out to another clip. And things like ASCII, extended ASCII Unicode, and the idea of metadata. Again, these type of things will probably break out. So ultimately, we'll have a few different clips to follow up on some of these topics. So let's see how far we can get with this clip. So PandA, you probably see it in the book also, is this idea of presence and absence, or PandA. So it's just meant to be what they call discrete. Discrete means very clear, distinct points, right? It's either a 0 or a 1, right? As opposed to something that is something in between, so shades of gray. So just like when you look at between 0 and 1, there could be infinite set of numbers that is between 0 and 1, right? It could be 0.1, it could be 0.111, so on and so forth, all the way through. But when we say 0 and 1, it's just going to be binary. Those are your only two discrete points. So that's what we mean here when we say discrete, distinct and separable. So there's no tiny gradations. Gradations is like what I was just describing before. Between 0 and 1, you can have 0.1, 0.11, so on and so forth to infinity. So we don't have that. And there's a little bit of a story behind that, but basically just from a processing standpoint, an automated processing standpoint, you need to have this idea of clear, distinct points to enable it to communicate effectively from a computer standpoint. Okay. So this covers a little bit more about binary. It could be anything, right? So over here on the right, you can see it could be true, false, 1, 0, on, off, yes, no, plus, minus. You know, basically two distinct opposite things that you can use to represent your two states, presence and absence. Okay, like here it says, you know, nothing says that one has to represent one thing or another, just as long as you're consistent throughout the system, right? So if the person sending the message and the one receiving the message are on the same page as to what 1 means and what 0 means, then you're fine. Of course, you have a problem if not everyone is thinking about the 0 and 1 in the same way. So PandA unit, known as a binary digit or a bit. Okay, later on we'll get into groupings of the bits, but for now, just remember a single digit will be a bit, right? And that's either off and on, 1 and 0, so on and so forth. So all this is just saying is that how the memory is organized is basically storing a whole sequence of zeros and ones within memory. And that's how it's set up to store data, how it's set up to pass the data around from you know, one person to another person, or one part of the computer to another part of the computer. So that's how it communicates in terms of zeros and ones. So you have the binary system, right? So it's what they call base 2 to represent numbers. So people are used to looking at things in terms of basically decimal, right? You have 10 fingers probably. So you can see things are set up in terms of 10. So we're used to thinking about things in terms of tens. So that's something that we would have to convert to make sure that we're communicating via the computer in a proper way in terms of binary. Okay, So all this is saying here is how many numbers you can represent. So if you have 1 bit, so n equals to 1, you can only represent 2 numbers, either 0 or 1. Okay, that's why you say you have 2 symbols here. You have 2 digits or 2 bits, basically it's 2 square or 4, right? So you can have 0, 0, 0, 1, 1, 1, and 1, 0. Okay, so those are how many symbols. So it grows in an exponential fashion. So the more of the digits that you have, or you add, or bits that you add, you can see it goes 2 to the 1, 2 to the 2, 2 cubed, so on and so forth all the way through. And then you can see the number of different symbols you can represent. Okay, so that's all this is showing here. You can see up top here, 0, 1, 1, 0, 1, 1, basically goes through and keeps on growing the more bits you add. Hexadecimal is base 16. Okay, so you can see, as it says here, the first digits here are basically what you're used to when you're counting to 10, right? So 0, 1, 2, 3, all the way up to 9, right? So those are all digits there that go up to 9. So that represents the first 10 characters of what you call hex. Now you can't go to 11 because that becomes two digits, or 10 or 11, I should say. So that's why you start going into alpha, right? So you start going to A, B, C, D, E, F, and that makes up the last 6 digits of base 16 of hex. Okay, so basically, you can imagine if I'm sending stuff on computer, it doesn't matter more or less how many bits you have, right? But it could probably get monotonous and error prone for a human to be looking at a whole bunch of bits. So by using hex, you kind of shorten that a little bit. So instead of having like 4 different bits that you're going to be looking at, you just have to look at 1 character. Okay, and we'll go into that in a little bit. But I'm going to, let me see here. Yeah, well, let me go with this before I cut this off. So you can see here, here's the 32 bits for a computer instruction. Right? And all you see is 1s and 0s, like I mentioned before. And as it says here, 0s and 1s is tedious and error prone. Right? So if you're looking at 1s and 0s, it's going to probably take you a while to understand what this is all representing. And if you're trying to transcribe this or copy and paste or whatever, whatever you're doing, you're probably going to have a chance of making a 1 a 0 and 0 a 1 by accident. Okay. So you can convert each of the 4 groups here, 4-digit groups here, into hex, and then you get a shorter version here. So this whole long series here, when you represent a hex, you can see it becomes much shorter here. Okay, so that kind of follows along what I just mentioned in the prior slide. Okay, so you're just mapping here, and I can explain more of this when we start going into converting stuff here. So you see 4 zeros, that's on binary. I convert that to hex, that becomes 0. And 1, and 2, and 3, and so on. Okay. In case you're wondering how these translate, right, instead of just memorizing it, but just understanding what all of these 1s and 0s means in terms of real numbers, I'll be explaining that to you in another clip. Okay, but all this is just meant to show you is how you can basically compress how you can represent a number from a binary to a hex representation. Okay, that's really all you need to know here. Okay, let me hold off on explaining ASCII until the next clip. Okay, stay tuned for another clip. Thank you.